Hi everyone, I'm going to lead a discussion about learning continuous facial action from speech for real-time animation. The main idea of this paper is to use speech to generate animation, and its algorithm is real-time. I will have three different parts to introduce this paper. First, I will introduce some basic knowledge, and then I will tell you how they implement these models. And finally, I will show you the experiment results. So the first part about basic knowledge. The main idea of this task is to use audio to generate 3D facial expressions. And also says this task is useful in human-machine interactions and it can produce a meaningful and pleasant feedback. So before I introduce this task, I want to show you some similar tasks. So there are some similar tasks that are talking head and talking face. That is, we can use text to generate talking face, and that is real image.
Text-based talking head video with a synthetic speech. You can observe the automatically generated facial expressions, rhythmic head motions, and upward
Renifanium. So So this can tell us that we can not only use audio to generate something, we can also use text to generate something. And as for the generate object, we can not only use the image based, and that is what we saw on the last slides. We can generate image, or we can also generate model.
talking avatar. 73 blend shapes, thought for speech and facial animation.
And this
Talking
And this is what this paper is going to do. This paper is going to predict this 3D model expressions. So how do we predict this this 3D model facial expressions? One very simple way is just to predict the parameters. We can use a pre-established 3D model and just predict parameters. So you can see on the right-hand side there are one pre-established 3D model, and on the left-hand side there are maybe 100 parameters, and each of one parameter can control a key point corresponding to the 3D model. So maybe this parameter can control the size of left eye, and this parameter can control the size of your mouse, and so this is what I'm going to predict. So we can use a vector to represent a face given a pre-established 3D model. However, the author of this paper they choose a different way to predict the 3D facial expressions. I want to remind you that we learned this facial action coding system in our class. The main idea of this system is to choose 46 different facial actions. And similarly, in this paper, the author chose one neutral face, this one, and 46 different facial expressions. And those 47 facial expressions are the basic facial expressions. So we can use a vector to represent the face. So for those 47 different facial expressions, we can also have 47 different parameters. So for neutral face, we can have this parameter. For the first expression, we can use parameter. For the 22 expression, we can have this parameter. And I want to remind you that different person can have different corresponding parameter b on the same facial expression. That is, maybe you and me, we also have a neutral face, and there are no other emotions on our face, but our parameter b are also different, because those parameters are corresponding to the key point on our face. So maybe this parameter controls the size of your eye, and this parameter controls the size of your mouse. So of course, we all have different face, so those parameter b are also different. But in this research, the parameter b are fixed, so they just give you a fixed face of this 47 expression. So now what are we going to predict in this research? We are going to predict the combination. We have 47 different phases and 47 corresponding parameters. So maybe currently my phase is like this one, and I can see that this phase is equal 0.5 times neutral phase plus 0.1 times the first facial expression plus blah 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 plus 0.3 times the 22 facial expression. And those red numbers are what we are going to predict. So when we use this way, we will discuss it in class on Tuesday. And now, okay, let's summary about the first part, about basic knowledge. We can use audio to generate 3D visual expressions. And I also show you an example that we can generate real image, and we can also generate two-dimensional animation. Besides this, we can also use text to generate other things, or we can also use audio plus text to generate same thing. And this task will mainly focus on use audio to generate 3D visual expressions, but on other similar tasks, you can use other different ways. So as for the pipeline, given the audio, we can first extract some meaningful features. We have two different ways to extract features. One is the traditional way, that is handcraft acoustic features. And another way is neural network. We can use an end-to-end model to extract features. And then we feed those features into a two-layered RNN. It can be LSTM or GRU. And finally, we need to predict those 46 coefficients. And those 46 coefficients are the right number we discussed before. So now let's move to the second part, implementation. And we mainly focus on the feature extraction part. So we said we have two different ways. One is handcraft acoustic features, another one is end-to-end model. So for the handcraft acoustic features, we also have three different methods. So first one is compare feature sets, and the second one is Gmap. For those two feature sets, we can use OpenSmell toolkits to extract them. So OpenSmell toolkit is a very powerful toolkit. You can extract compare feature sets from functional level, from LDD data level, or from low-level descriptor level. And we can also use male-scaled spectrogram, MFCC, and chromogram to extract meaningful features. As for the loss function, we can use a L2 loss function. So this variable is corresponding to the coefficiency we predict, and this one it's a ground truth. So we just want to our predict number is very close to the ground truth. And as for the neural network method, given the input audio, we can first use FTT to translate it into the spectrogram and use a convolution network to extract meaningful features. And one important thing you need to notice is that this is not a two-dimensional convolution layer, it's one-dimensional convolution layer. So first it apply a convolutions on frequency level, and then it apply convolution on time level, this one-dimensional layer. As for the loss function about this end-to-end model, we can also use L2 loss function, but also found that if we use this loss function, the model only focuses on lip and ignore other emotions. So I want to remind you that we have one neutral phase and 46 different emotion phase. Maybe you can tell the difference between this phase and this phase because they are obviously different. But can you tell the difference between this phase and this phase? It's a little bit hard, right? So most impressions are subtle. So maybe you can really tell difference between them. And we want to predict those right numbers. So maybe for this number, for the uppermost coefficient, the parameter are between 0 and 1. So the neural network think, oh, okay, it's important, so I need to pay attention to it. But for other facial expression parameter, because maybe for ratio left check, its parameter are only between 0 and 0.05. So the neural network think, okay, it's not that important. Maybe I can just predict it as 0. And that's the reason why we need a new loss function. So we introduce a new loss function. We use standard deviation to remove bias, and we use this L1 to encourage sparsity. Okay, let's summary about our second part. So we introduced two different models. One is handcraft acoustic feature model. So given the audio, we can use traditional method to extract meaningful features and use RN to handle those features and predict our results. And this is the loss function. We use L2 loss function. As for the N2N model, given the audio, we use FDT to translate into the spectrogram and use one-dimensional convolution layer to extract meaningful feature and use RN to predict 46 parameters, 46 results. And we use this different loss function. Okay, let's come to the third part, experiments. So they used 5 different datasets. The first 3, they are similar. They use them on the trained dataset and also test them. As for the grid dataset, they it is only used in testing, so they want to use it to test generalization across datasets. And as for the GMAP dataset, it uses branch, so they want to use it to test generalization across language. So as for the evaluation protocol, we use 3 different protocols. And as for the models, we have 4 different ways, 3 traditional way and 1 neural network way to extract feature. And we have many different RL models. So that means we have tons of different models, and the author test them. Here's the result. So the results show that they have 2 findings. The first one is that CGLU, that is, use the N2N model plus GLU is the best. And they also found that GMAPs, and that is the one method to extract features. So GMAP features is effective at modeling subtle emotions. As for the real time, we'll leave the discussion about this in class. So okay, let's summary about this paper. So we want to use audio to generate 3D facial expressions. And we have 2 different model. One is handcraft acoustic feature model, another one is N2N model. And they found that GLU is the best, that is, use this N2N model plus GLU is the best. And the second one is that they implement a real-time algorithm